Hello everyone, welcome to Mindspan Education. This is a continuation to this series of lectures on subject calculus and optimization as part of our Get DA complete course for 2027 aspirants. So this is a continuation of the previous lecture where I was discussing the domain and range of a function and what is domain, what is range, what is function itself, how we define function. All these things we have already covered in the previous lectures. So I would recommend you to go through them before watching this lecture. In this lecture, what we are going to see is we will see, uh, as you know, it is relatively easier to calculate domain than the range of the function because uh, as input of a function, we can apply some algebraic restriction constraints that are universally accepted, like denominator cannot be zero, uh, uh, a square root function cannot take anything less than zero. All this restriction we can apply and find the we can find the input of a function, that is domain. But for range, we don't have those privilege. For range, we have to apply some technique, some calculus method, some algebraic method, algebraic manipulation of the expression to find the range of a function, to predict at least what will be the possible output of a function. So we are going to cover those techniques in this lecture. Very important for GATE aspirants. And second thing that I'm going to cover is composite functions. That is also part of single variable function. It is called composition of functions. Like when multiple function gets in the form of FOG or GOF, you might have heard. It is called composition of functions. What is composition of functions and how we calculate domain and range? What are some points that we need to keep in our mind while calculating the composition of a function? All these things we will discuss and we will take few examples in this lecture. Okay, so let's start. First thing is techniques to find the range of a function. Okay, so first technique is algebraic method. Okay, algebraic method. Under this algebraic method, it is also called inverse thinking. In inverse thinking, like if we are able to somehow convert convert this range in the form of domain, then we can apply all those techniques that we know about the domain. Okay, so what we do is first, suppose this is our function y equal to fx. Suppose this is our function definition. Then we express this in such a way that this expression becomes x equal to f of y. We apply all the algebraic method that are available and we express x in terms of y. Now this becomes another type of function where this x becomes expression of y. Now if you forget about this original function for a moment, then for this particular function, y is domain, right? Y is domain. And we can apply all the constraints that are available for a domain. Although log cannot have anything less than equal to 0, denominator cannot be 0, a square root function cannot be less than 0. All these things, restriction we can apply on y to predict the values of y, right? By applying all those things, whatever value we calculate for y, they becomes a range of the original function, since y was actually range of the original function, output of the original function. Okay, for example, if we consider this function y equal to x minus 1 by x plus 1, then what we can do, what our goal is to convert this expression in such a way that we can get x equal to some expression of y. Okay, now for that, just do the cross multiplication. then what we are going to get? Y into x plus 1 equal to x minus 1. If we multiply this, then we will get y into x plus y equal to x minus 1. Again, further, what we are going to get? Y into x minus x. We took x this side and y right side. So what we are going to get? Y into x equal to minus 1 minus y. If we solve again, what we are going to end up with? X equal to minus y plus 1 over y minus 1. This is what we are going to get. Now, if you forget this y equal to x minus 1 by x plus 1 for a moment, then for this function, y is the domain, y is input, right? Input. Now, for this input, restriction is sorry restriction is that denominator cannot be 0. So y minus 1 cannot be 0, which will give us y cannot be 1. But remember what y was? Y actually was output of the our actual function that we had taken. So y cannot be 1. That means the range cannot be 1 for our original function. Output cannot be 1. So we can say that range of our original function is all real number minus the set 1, means except 1 we can get anything as output, right? So this is called algebraic method. Here we manipulate the expression in such a way that we write x in terms of y, so that we can apply the domain tips and tricks on y to predict its values, and that y is basically the output of the original function. So we can find the output of the original function. Okay, now second technique is, if function is like this, simple expression, then we can apply this. But if it is quadratic expression, then it is relatively hard to express like that. So what we do is, what we can do here is, for let me take pencil. Okay, for quadratic expression, what we can do? It is called completing the square. Completing the square. Let's call this. Okay, what we do here? Suppose we have an expression in this form. Let me change the color. Suppose we have an expression in this form, y equal to ax square plus bx plus c. Then what we do here is, we try to write this in this simple form, y equal to, let's say, x minus a whole square plus b. Plus b, okay? In this form, we can write it like this, right? By doing algebraic plus and minus, all those things, we can write it in this form. For this form, if we try to draw a graph, or we can simply here intuitively analyze that this portion is a whole square. It cannot go anything below 0, right? So this portion, minimum it can go is 0, and this is a constant. So overall y, this will not change. This will remain a constant, and this portion will minimum go to 0, which means y minimum will go to as 0 plus b is b, right? B. And maximum it can go anything. Since this is a square, it can go till infinity. So maximum it can go till infinity, right? So minimum range means the minimum and the maximum of the output that we can get, provided that the function is continuous. This function is continuous. Okay, all polynomial functions are continuous. Okay, now so we can say that range here will become from b to infinity. Later on I will show the graph of this function that will also prove this hypothesis. Okay, now for example, let me write it clearly. Okay, plus b. So this portion minimum can go 0, right? So y minimum can be 0 plus b, which is b, and y maximum can be infinity, right? So we can say that this gives us a range as b to infinity. Okay, we can write properly like this. Okay, so this is called completing the square. We write it in the form that we already know. If we look at its graph, then you will get more clear idea. If you draw the graph of this function, then the graph will give you minimum and maxima more clearly. If we say this y and this is x, normal graph of y equal to x square is like this. It goes through 0. But for this particular graph, y minimum becomes b. So suppose this is b. Okay, this is b. So minimum y can come here, and uh, where it will come at x equal to a. When we put x equal to a, then this part will become 0, right? 0. There it will give b. So at x equal to a, suppose this is x equal to a. Okay, suppose this is b and this is x equal to a. Then this is our graph, right? And this point is basically a and b. The coordinate, this coordinate is a and b. So minimum, if you see this graph in perspective of y, minimum it is reaching is at b, and maximum it is going till infinity. So range clearly becomes b to infinity, right? Okay, now another method. Another method is called using inequalities. Okay, using inequality. What will be here? For some standard method that we already know that it cannot take below something, and it cannot take give above some number as output, we apply those techniques. What I am saying is, suppose say we know that sin x, let's say sin x always remains restricted in -1 to 1 as output. Okay, similar other functions like x square always remains restricted above 0 or including 0, right? So if we get an expression like this, y equal to 3 sin x 3 sin x plus let's say 2, right? Then how we can calculate range of this function? We apply inequalities. Means sin x will be always greater than -1. So this portion is always greater than 3 into -1, and greater than equal to, and it will be always less than equal to 3 into 1, right? So this will be always greater than equal to -3 and less than equal to 3, right? So minimum it can go till -3. and maximum it can go till 3, right? So using these inequalities, we try to deduce the actual fluctuation in the output of this overall function. So it can go minimum till minus 3 plus 2 means minus 5. Oh, sorry, minus 3 plus 2 minus 1. And maximum it can go, this is minimum it can go, right? Minimum. And maximum it can go till 3 plus 2, which is 5. So minimum minus 1 and maximum 5 for overall function. So we can say that the range of this function is from minus 1 till 5. There is no uh, uh, doubt in saying that range is from minus 1 to 5, right? So what we did here, by knowing already some restriction of a function based on their maximum and minimum values, using those inequalities, we try to replace it in the expression to find the overall minimum and maximum of the function, right? So this is very basic example. It is very useful in even more complicated examples. We will see those examples later on. Okay, this is maximum, right? Okay. And similarly, you can use this x square greater than or equal to 0, this inequality, and others that are available like log x and all those things. Okay, no, log x has everything as output. We cannot use that. Okay, now uh, another method. Another method is graph based. Finally, for whichever function we can draw graph, we should draw a graph. Okay, graph based. For example, whatever the example I gave in the last to last example, suppose y equal to x minus a whole square plus b, then even a rough graph of this function will give you an idea that the domain and range of this function will be suppose this line is x equal to y equal to b, this is x and this is y. Okay, and suppose this line is x equal to a. So this graph is upward opening parabola which touches here at point A and B. So we can say that minimum, if we analyze this graph in this direction, in y direction, minimum value that y is taking is minimum is B, and maximum that y is taking is infinity. So range will become B to infinity, including B to infinity. Okay. Now, even if you are not able to draw the exact graph of the function, even the rough graph, a rough idea about the function's nature will give you enough information that you can eliminate the options, other options which are wrong. Okay. For gate perspective, it is very important that you apply elimination method. So the wild options which are not falling in the range will get eliminated even if you draw a rough graph of the function. Okay, so these are the techniques that you can use. First technique, algebraic method, Most of the problem will be solved using this, or make it y equal to x square format, or use some inequalities whatever available in the mathematics. Use those inequalities to predict fluctuation of the overall expression. More you practice on these examples, more you will get ideas. Okay, or using graph for any uh, you can say popular functions. You can draw the graph. Even rough graph will give you enough idea to eliminate wrong options. Okay, now I will take one example uh, on the range, how we use these things. Okay, let's take an example. Sometimes we also use derivatives, like we don't have any space here. We can write here, if we make this point d, derivative, to find nature of function and its maximum minimum points. Using pure calculus, we can write right like this, and this point will become E option. For later on, what we are going to see, the maximum minima, that optimization of function. There we will see we can calculate maximum and minimum value of a function based on its derivative, double derivative of all those tests. We can calculate maximum and minimum value of a function. We can use those technique also to calculate predict range of a function. Okay, using that method also we can calculate. Now let's take some example on range. Suppose our function is fx equal to x square minus 1 over x square plus 1. Now we have to be very cautious, and more you practice, more you will get experience in calculating the range. Okay, here this function at first end it seems very complicated, and we might try to go into the derivative method and try to use heavy guns like dy by dx and heavy calculus, but those things are not needed here. Okay, how we can solve this, you can see. let let t equal to x square. If we assume t equal to x square, we are going to replace this. Then what we are going to get condition here, that since x square always remains greater than equal to 0, which will give us t greater than equal to 0 always, right? Don't forget this. We are going to use this property, okay, later on. So f, so if we solve this, what we are going to get, just a second. Let's write it in the form of y. Okay, otherwise we we will not able to do cross multiplication and all. Okay, y equal to x square minus 1 over x square plus 1. Now if you write it like this, then what we are going to get, f, not f anymore here, okay. uh, let's remove this. Okay, Now what we are going to get, if we replace with t equal to x square in this function, what we are going to get, y equal to t minus 1 over t plus 1, right? If we calculate this by cross multiplication, then what we are going to get is y into t plus 1 equal to t minus 1. If we simplify this in terms of t, what we are going to get is t equal to, finally we will get minus y plus 1 over y minus 1. Okay, we already had this kind of example just a couple of minutes ago. Okay, so this is our new function. This is our new function for which we are going to apply domain restriction. Okay, first what we are going to apply is that our t must be greater than equal to 0. T must be greater than equal to 0. So let's apply it here. We can say that we can say that since t is greater than equal to 0, so we can say that minus y plus 1 over y minus 1 is greater than equal to 0. Okay, we'll use this expression and we will build on this. Okay, now we will apply wavy curve method that we have already seen in previous lecture. Okay, to find the exact critical points and everything. So first thing about that method is we should not keep any y coefficient as negative. So this will become y plus 1 over y minus 1 less than equal to 0. Since this minus we removed, so inequality sign got changed. Now for this we can write that critical points are minus 1 and 1. Okay, critical points are the points where this function might become 0. Okay, now if we plot this on the number line, what we are going to get is this method what I'm using right now is called wavy curve method. Okay, in the first or second lecture I have explained this in detail. You should go if you are unaware of this. This is our number line and points are minus 1 and 1. Okay, now take any point greater than 1 and try to predict its value. Let's take a very large number 10. 10 plus 1 positive over 10 minus 1 also positive, means this remains positive. Suppose this is positive part, then this curve will go here, like anything greater than 1 it will remain in the positive side. At this particular 1 which comes because of y equal to y minus 1, because of this factor y minus 1, its power is odd. Okay, odd means 1 power. So direction of this curve will change, it will go below, like if it was above this number line, it will go below this number line, and this is negative part. And this minus 1 is coming because of y plus 1, its power is also odd 1. So again the direction will change. If it is a negative side, it will go to positive side. Okay, now what is our goal is this overall expression should remain less than equal to 0, means only the negative part is our focus here, negative part only, this portion, right? In this portion where the curve is from minus 1 to 1, so we can say that y is from minus 1 to 1. Now at 1 We have to give open bubble. Open bubble means we cannot put this one, otherwise this machine will break. Okay, we cannot have y equal to 1. So 1 cannot be part of the answer, but minus 1 can be. But what y actually was, let's see. Y was our range. This is our y. This is our y. Okay, y was actually our range, our output. So our output can be from minus 1 to 1, which means our range will be will be from minus 1 to 1, right? From minus 1 to 1. Okay, so now see how easily we were able to calculate the range of this function. If you go into the calculus method and other thing, you might get lost in the lot of calculation and all those things. It will take more time. So it won't take time since I wrote every expression and tried to explain. That's why it took some time. Otherwise, you can uh, find the range in 40-50 seconds. Okay. So this is just an example how we use all these techniques. Okay. Now we'll take more examples later at later point. Now we will move to the next topic. Our next topic is composition of function. Okay. Composition composition of functions. More popular name is fog, golf, fof, all those things that we know these functions from those. Okay, let's say how we can understand what composition is. Let's say we have a one fx as first machine. Let's say what machine means. Let's say let's assume is a machine, right? Machine which takes input and gives out, right? Now we have assumed that function is a machine which takes some input and give some output. There is no harm in assuming this since that is what function does. Now if we say that if we say that fx is first machine, first machine and gx is second machine, then by composition what I mean is, then composition is defined like this. FOG, suppose we are composing it in this way. FOG of x equal to f of g of x, suppose like this. Then what it is trying to say essentially is first machine f of x, output second machine g of x, g of x, then another output. Okay, this is input of f, right? Input of f of x, and then its output becomes input of g of x, and the final output comes from sorry, I wrote it in opposite way. So let's just write it G and F. Okay, since G is inside, means G should get the first input, G of X and F of X. So input of G of X and output of G of X becomes input of F of X. And the final output from F of X is the output of the composite function. This is what composition really means. Whenever we give input, we give it to the inner function. Whatever inner function is, we give input to that function, and output of that function becomes the input of the outer function. It can be multiple composition, no, not necessarily only two. It can be f of g of h of k, like that. So starting from right side, if we try to evaluate, then the input of rightmost will become output of the next function, then output of the next function will become output of the second next function, like that. Okay, in this fashion we evaluate this f of composition of a function, right? And one thing that we need to keep in mind, that order matters in this case. Order means in which order we write f of g or g o f. It matters in this. They are not essentially equal. What I'm trying to say, I will give you example. First, let me write this note. While watching, if this video becomes slow for you, you can watch at 2x or 1.5x. Okay, since I'm writing this things, it may become slow. Okay, order of composition matters, which means, what I mean to say, f of g of x, which is f of g of x, is not equal to g of f of x in other reverse order, which is equal to g of f of x. They may be equal in some cases, but in general, they are not equal to. Let me write here in general. Why I'm writing here in general? In some cases, functions are defined like that. The expressions are in such a way that they might be equal, but generally they are not same. Okay, they are different. I will give one example to get a better idea. Okay, so let's take an example. Let's say f of x equal to x square and g of x equal to x plus 1. Simple example, okay, to understand this. Now, if we calculate f of g of x, then what we are going to get? F of g of x. So first it will get gx, okay, then that value will go into f of x. So f of gx, what is gx? X plus 1. So we have to put x plus 1 as input of fx. So what we are going to get? X plus 1 whole squared. Okay, this is f of g of x. Now if we calculate g of f of x, then what we are going to get? G of fx. So first we will get fx, means x square. Then we are going to get that this x square will become input of g of x, which is x plus 1, right? Now, so this will become x square plus 1. You can see here clearly that these two are not equal, right? One x plus 1 whole square, another is just x square plus 1. So they are generally not equal. Okay, and this is how we calculate this. Now, so for this function, if we talk about domain and range, then what we are going to get? Domain, domain and range of composition of functions. Composite function. Since it is like this, f of g, so composition of function is not always f of g. It can be on self itself, like f of f also. F may composite on itself, f of f of f, like this also. So it is not always like f of g or g of f, like this. Okay. Now, if function is like this, f of g of x, then while checking the domain, what we need to keep in mind is, if our composition is f of g of x, then for domain and range, for domain particularly, what we need to keep in mind is all values of, first, whatever input is allowed for f, that input, that only we can put in f of g, right? Otherwise, whatever input is allowed in g, right? First time we are putting into g. Okay, all values of x such that it should follow, such that first thing, x should be part of domain of g, right? Otherwise g will break domain of g. First time where we are putting x in g, right? If we apply like this, if this is g and its output is going into f, this is g and this is f, then all the input that is allowed as domain of g, and then first thing is this, and second thing we can say that gx should be part of domain of f, otherwise it will break f, right? Okay, now let me explain what I meant by these things. While calculating the domain of composite function, we have to apply these two important rules. First, the input should be part of the domain of g, the first function where we are putting the input, which is very uh, self-explanatory. Okay. Now, second thing, whatever output we get, it should be in the part of domain of f. Since this output of gx is becoming the input of f, that's why gx का जो आउटपुट है वो f के डोमेन में होना चाहिए. अदरवाइज ऐसा आउटपुट ये ना दे दे जिससे कि ये f के डोमेन में ना हो, तो फिर ये f ब्रेक कर जाएगा, तो हमारा कंप्लीट जो कंपोजिट फंक्शन है वो ब्रेक कर जाएगा. तो ये दोनों रेस्ट्रिक्शन हमें लेके चलना पड़ेगा ये डोमेन कैलकुलेट करने के लिए. मोस्ट ऑफ द लोग ये वाला पार्ट भूल जाते हैं, जिससे डोमेन कैलकुलेट करने में मिस्टेक हो जाता है। ये क्या चीज है हम अभी एग्जांपल लेके देखेंगे। विल सी दिस बाय एन एग्जांपल। ओके, लेट्स टेक एन एग्जांपल। Let's say we have let's take some good example so that we can show what it means by that. Let's say, let's take this example. Fx equal to 1 by x and gx equal to x minus 1. Okay, this is our example. Now if we calculate f of g, if we analyze f of g domain, if we are going to find domain of f of gx, then what we can say, if we blindly see that g is the first function, whatever g accepts, f of g will also accept, then we can say domain of g is all real number, right? So we will blindly say that domain of f of g is all real number, but that's not the case here. That is what I'm giving more emphasis on. Now if we calculate f of g, then we can say that f of gx, right? So it will become f of gx is x minus 1, which will become 1 over x minus 1. So see, it does not accept x equal to 1 at all. X equal to 1 will break this function. So we can say that x cannot be equal to 1. Even though gx is accepting all the real number as input, which is the first input function of composite function, this composite function f of g, but x equal to 1, even though gx is accepting x equal to 1, but f of x is not able to accept whatever gx is giving output on x equal to 1. That's why we cannot put x equal to 1 as overall input of this composite function. I hope you understood what I meant by this second point. Okay, we can only put input so that the output of the first function should not break the next function. Okay, and this does not apply only for two function. If we have many more in the line of composition, like f of g of h like this, then it applies for everything. Anything input in h should not break g, should not break f correspondingly, right? Iteratively, whatever output comes from h should not break the input of g. Whatever output comes from g should not break the input of f, like this. Okay, so iteratively, in that fashion, we can calculate the domain of this composite function. So we can say that here domain is r minus 1. We cannot put 1 as a input, right? So this is what I was saying. So for this composite function, uh, basic introduction I gave. More example we will take later, and I will try to put some better examples in the practice problem section, which you can go here at minusfuneducation.com and do the practice. More you practice, more you become comfortable in these topics. Okay, so in this lecture, let's keep this much only, and we'll start next topic in next video. Okay, thank you everyone. Happy learning. And yes, do practice. Okay, all the practice problems I have already added, and I will add as the topics gets covered. Please do the practice at mindspaneducation.com. All the these are only basic problems to cover, to introduce the topic, to let you get familiar with the concept. But the actual problems that test your knowledge or your understanding. I'm putting those problems in the practice problem section. You can say quiz section, which you can give here at mindspaneducation.com. Okay, so yes, thank you everyone.